Okay, bueno. Let's share. Shrink that. All right, let's try that all over again, this time with feeling. So we're going to discuss the common parts of a line plot and a few other things. There are some specially invented words for plotting that were invented to keep the people that draw things employed. So the two that we're going to see is ordinate and abscissa. Those are big fancy sounding words for the left, right, and the up, down axis. So I prefer left, right, and up, down because that works, at least on this planet, as long as you're oriented correctly to the center of the planet. Then we will define the usual convention for plotting observations against models. It's pretty simple. And talk a little bit about legends, which is how you describe what's in the plot. It's not the most awesome plot you've ever seen that will live on for centuries, which would be a legendary plot. But first, Matplotlib. You've seen this before. This is yet another external package. I'm sure when Josh does his lab today, he'll say this is another external package with no particular broad thing in mind. It does have a broad thing in mind because you have to communicate your findings to other people. Supplying them with equations is not very effective, as you well know now, because we supply you with equations in your math classes and engineering classes. They're cool and everything, but it's not a super effective way to communicate. We could try it in writing, but I'm looking at your lovely Monday morning faces, and you've read like 3 words on that, maybe the purple ones, and your brains check out. But pictures work. And pictures are used both in scientific and in persuasive communication to share an idea with a recipient. Matplotlib is a collection of functions that helps us make pictures, plot pictures as opposed to images. And it makes it work like Matlab. Each function within it is in a sub package called pyplot. I assume that means Python plot, and it allows you to make some change to a figure. So we can create a drawing area. We can tell it what to draw. We can describe axes. We can change markers from triangles to circles to squares and paragraphs in the back explaining each one. And at some point when we've decorated our plot, we issue the show plot command and it renders it to the screen. That's all been happening in the background with the scripts that we provided you in your labs. For example, make a plot. It just does all that, and all you have to do is call it correctly. The nice feature of Matplotlib is it maintains the state of the plot across repeated function calls. So until you change the state, so until you change what axis, you change what list is being plotted, it will preserve that at least until you exit the program. Axes here, and in most cases in the documentation, refer to the axis part of a figure and not necessarily the strict mathematical term for more than one axis. All right, so let's look at some graphics conventions for plots. So ordinates, abscissas, dependent and independent variables. The abscissa, unless told otherwise, is usually the left-right axis, the horizontal axis. The ordinate is the up-down axis, the vertical axis. And currently we're going to take a computational break because the bits were a little tired from playing around all night last night, practicing their cyber warfare. When we describe the models themselves, the things that we're plotting, we have our independent variable. Usually that's plotted on the left-right axis. It also goes by the name explanatory variable, predictor variable, feature, if we're using modern terminology. It's a variable that is controlled or manipulated in an experiment or some theoretical analysis. So that's a variable that we are changing, and we want to know how the thing's going to respond to that. The dependent variable is the response variable or the prediction, etc. And that's the variable that's measured or observed, presumably as a function of the independent variable. Let's think in physics. We have that wonderful model, force equals mass times acceleration. Of those, probably the thing we have some control over is mass. If we get too much mass, you just cut off an ankle or something or a leg, and you can change the mass. So if we're trying to determine the force on something, mass is our independent variable. That's what we get to adjust by adding and removing body parts, and then everything else is predicted by the model. So let's suppose the acceleration is constant. If you double the mass, what do you expect to happen to the force? It doubles. If we half the mass, the force goes to half. If we cut the mass low enough, it's just a puddle of muck and nothing's alive. So the mass is our independent variable, force is the dependent variable. And in that particular thought example, the coefficient of correlation was the acceleration. That's what related the two. Okay, so in most cases in plotting, the independent variable is plotted on the left-right axis. Not always, but most of the time. And if you have no other external reason to not do that, that's as good as any. Sometimes in water world, we plot depth on the up-down axis, and that's actually the independent variable, and it's predicting something else. But usually it's on the horizontal axis. And then the vertical axis is where we plot the response. So in the case of our grisly mental example, our horizontal axis would be mass, our vertical axis would be force. So if we increase the mass, the force goes up. And there's a fairly obvious pictorial relationship between the two, which is the whole point of graphics. So here is a picture from somewhere, from Thinking Like an Engineer. It's an active learning approach from 2018 Pearson Products Incorporated. The apps is, so if this were presented to you as in a quiz, you wouldn't have the answer there. You'd get a varied quiz to determine whether you stay in engineering or you move back to the business school. And if you were asked, is the abscissa A, the horizontal axis, or B, the vertical axis? With no additional information other than what I just said, what would you choose? Oh, please, somebody. It's right there in the answer. A, the horizontal axis. That type of question presentation is called a who's buried in Grant's tomb. So conventions for proper plots. Proper is my value judgment. That's probably not the best word. So most plots, you need to have a title or a caption. A title is normally put at the top of the plot. Let's see if that last one had a title. It did not, but the title would go up here. A caption, you've seen it in your other documentation. They'll usually say figure 1, plot of blue dots and red dots, something like that. That's a caption. Title is conveying the same kind of information. A plot should have one or the other of those. You could put both, but you don't get double bonus for that. It's not like gambling in Las Vegas, where if you put a caption and a title, your jackpot is increased thirtyfold. You should label both axes clearly. I love it when you see words like that, because I don't know exactly what they mean by clearly. Label both axes so that the reader can see what you're trying to describe. For scientific or engineering stuff, you want to include the variable name in the axis label, the variable itself, and usually the unit. So for example, mass and acceleration are thought experiment. we would have the horizontal axis would be mass, comma, M, and then what units? Kilograms or grams or grains. I can't remember the weird mass units. There are some strange ones. And so this graphic here is conveying that same information. What you want to include in the axis labels is what is being plotted, what's the symbol for the variable, and what are the units. For example, time, t in seconds, density, rho, and in grams per cubic centimeter in this example, or kilograms per cubic meter, which is basically the same unit. Use a descriptive title or caption within the document, and when you're describing the graph, because if you're putting a graphic in a document, you can't just stick it there. If you write C figure 3, that is the rudest thing you can do as an author to another human being. So when I see that in dissertations or master's theses, it instantly goes, it doesn't really go to the trash can. But I quit reading because that is rude. Figure 1 is a plot of mass versus force for a typical human being with body parts added. That's what a descriptive narrative thing should be of a plot. And actually, if you want to just memorize stuff, figure 1 is that's all you're trying to answer with the descriptive part. But if you put C figure 1, a lot of your textbooks say C figure 1. They're just rude to you. They don't respect you. That's why they're charging you $150 for something you should be able to get for 40. But I will pontificate now while I can. Try to show respect for the poor suckers that got to read your work. They don't want to read it, so might as well at least be as respectful as you can. If possible, you want to select increments on the X and Y axis that make it easy to interpolate your information, because chances are the reader of it, if they're actually going to use it, are not going to be lucky enough to have a value that exactly falls on one of your plotted markers. It'll be somewhere in between. So oftentimes, typically we do increments of 1, 2, 2.5, 5, or 1 through 10, mostly because those can scale by powers of 10 up and down pretty easily. Generally, you don't want to use weird increments like 3, 7, 15, or 6.5. If it's a logarithmic scale, they're going to be weird by default. But unless there's a really, really good reason, you won't plot 3, 7, 15. There might be a really good reason on some instances. And the really good reason is not, it was the only plot I could make actually work. That's not a really good reason. Usually you're going to want to include grid lines. I don't think many of my examples have them. I'm going to have to read how to do that. I don't actually know how to put grid lines in a Python plot, but it can't possibly be that hard. And we're normally plotting either experimental data or a model. So there it says theoretical data. That actually is an oxymoron. That doesn't make sense. Data is real, so it can't be a theoretical data. It's a model. It's a data model. So try to get in that mental habit. You have to live with whatever they provide you. So experimental data usually represents measurements or observations. By convention, they are shown as discrete markers. So here we have some discrete markers. I think this is diameter versus power. Let's see. There was never a measurement made between these two red markers. So that's why they're shown as discrete markers. If it's observations, you only show where the observations were made. Now we may go back and produce a really nice model. Because it's a model, you can predict the value anywhere on the line. So by convention, observations are markers, models are solid curves. Any questions on that? It's pretty straightforward. It's It's as close to no brains required as you can get. Use the portrait orientation when making your plot. That doesn't matter so much with PyPlot. Make it large enough to be easily read. And if more than one experimental data set is plotted, we have to take a 5-minute break for the computer to catch up. Come on, Bits. I know you're in there. I can see you. Use different shapes for each data set and use different colors. And in that case, you also need to include a legend that's explaining which shape goes with which data set. Okay, the reason we use different shapes is you have no guarantee that the reader is going to actually be able to render your plot in color. It might just be in black and white, in which case, when you take something in color and you put it on a Xerox machine, or Xerox if you spell it the way it's actually spelled, and produce a black and white copy, what color is blue in black and white? Black. What color is red in black and white? Black. What color is, you get my point. They all look the same. So we use symbols to differentiate between different things with the intent that they might actually be printed in black and white. On the computer screen, usually that's not so much of a problem because modern ones by default almost always produce color. Avoid colors that you can't see. So there's yellow right there, or light blue. And actually that came out really good in the presentation because those are barely visible in the projection. Now in lab, Josh, flips the background to black, so those probably would show up pretty good. Include a legend if 2 or more data sets are presented. You don't need a legend for a single data set, but you should include meaningful series names for multiple data sets. Here's an example of what's considered a nicely drawn plot showing experimental data. And let's look at the annotated parts. We've got a left-right axis and an up-down axis. And I'm guessing this is a plot. We don't have a title, so it's not completely correctly drawn. Let me check that there's no title. Yep, so -1 for the drawer of this, no title. But I think it's associating height with power from a wind turbine. We can pretend that for the sake of today's discussion. So what is the predictor variable? Anybody? It's a consonant. Height. What are its units? Yeah, it looks like meters. Its units are amps in this case, but that's probably meters. What is the response variable? Power. Its symbol in this case is capital P, and it is in horsepower. Everybody knows that you mix SI units of meters with US customary units of horsepower. That's just the way you do stuff. So we see our horizontal axis is ranging from 0 to 120 in major increments of 20, and in minor increments, these are going to be increments of 4. So the grid is perfect, but it meets our obligatory construction rules. We also have a legend down there to the right. So the red rectangles are mass of 250 kilograms of something, and then the blue diamonds are mass of 100 kilograms of something. So there are 2 sets of observations plotted on there. So if I was to ask you, if you want to increase power and the only thing that change is mass, what would you choose? Does more mass make the power go up, or does less mass make the power go up? Look at that, less mass. No, you don't know what this is talking about. You can interpret the graph. Why? Because it's drawn correctly. These boxes with labels on it don't appear in real graphs. Because the data are experimental, they're markers only. And on the label axis, don't overdo the stuff after the decimal point. So you can order the plot to go 0.2500, but that would be an act of dumbness because in addition to using up real estate on your computer screen, it's not very informative and will make your reader angry. In this case, horizontal and vertical grid lines are shown, and actually minor grid lines are also plotted. Generally, the minor grid lines are optional. I can't come up with a great reason why they're useful here, but occasionally it's useful to have the minor grid lines. Now here's an example of a plot that shows models, model data. It says theoretical data, but there is no such thing as theoretical data. In theory, we're perfect, but in practice, we're observation. So showing a model. In this case, horizontal axis is mass in grams going from 0 to 60. Vertical axis is density in grams per cubic centimeter, going from 0 to just shy of 2. Vertical and horizontal grid lines are shown. Axis label includes variable in the unit. Appropriate symbols are used for abbreviations. Axis scale is set to reflect the actual size without additional decimals. There's only one data series, so we don't need a legend. You could put one if you want. If you're like me and intentionally lazy, you code up a function that makes plots for you. Probably always have a legend, so just live with it, or if you don't modify. In this case, because the data are a model, because this is a data model, it's shown as a line, model line. So assuming the model is reasonably useful for whatever it was used to fit it. If I were to ask you what is the anticipated density of something that weighs 35 grams in this particular context, you would tell me it is roughly 1. Excellent. So you're able to answer that question because it's an effectively drawn communication device. I'm sure we could come up with an equation that does the same thing. That would be harder to interpret that fast. You could certainly do an equation, but you would have to put the 35 grams in to form arithmetic. This way you can just look at it. That's the point of plotting, is to be able to visually communicate an idea fairly rapidly. So now we'll introduce to our friends. Good, we're good on time. Matplot library. So the high-level library is called Matplotlib. I don't actually know what it stands for. Truth, Justice, and the American Way, of course. But that's also super duper neat. And then it has sub-libraries in it, and the main one we use is PyPlot. So to import PyPlot, you import matplotlib.pyplot. And you can elaborate on that. You can use aliases and so forth. So we'll make a line chart. A line chart or a line plot or line graph or curve is a type of chart which displays information as a series of points called markers connected by straight line segments. So a line chart is, well, I'll just leave it at that. If you played in Excel, when you do the line chart or the scatter plot and you don't choose smoothing, that's an option in Excel, it puts the markers down and then it joins them with a straight line. And so curved things look a little bumpy. They kind of look like how I drive because I'm only awake a few seconds per minute. And that's when I use it to do that navigational changes. It's a basic kind of chart common in lots of fields. It's similar to a scatter plot, except that unlike a scatter plot, line charts by default have ordered information. So the x-axis and y-axis generally are ordered with respect to each other. It's used to visualize trends in data, often over intervals of time. If that's the case, it's called a time series. And in such instances, the chart would be organized chronologically. So less time to the left, more time to the right. We'll look at an example in a second. The x-axis spacing can sometimes be tricky, and line charts in the hands of an expert can be used to intentionally deceive. In the hands of just learning how to use it, you can unintentionally deceive either yourself or other people. So be careful, that's the chart that you want to use. So here's an example. So we have two lists here. We have a list called elapsed time in seconds and speed in meters per second. I think we may have done this in lab already. So we have elapsed time as 0, 1, 2, 3, 4, 5, and 6 seconds, and then we have various speeds associated with it. So if you were to look at just that tabular information, what can you conclude about the speed of the object as time progresses? It's increasing. Does the acceleration appear to be constant? I would say no. I don't think it's constant. I think acceleration is changing too. How do you come up with that? Acceleration by definition is the change in speed with respect to time. So if we just look at 2 points, for example, between second 0 and 1, the speed has changed 3 meters per second. But between 5 and 6, we've gone from 30 to 45. The speed has changed 15 meters per second. So the acceleration does not appear to be constant. That's about all you can get out of the tabulation. Let's instead just plot it. So to plot it, we can import the Matplot library. I'm not actually going to run it. I'm just going to go through the notes. I assure you it would probably work if I cut and paste, but you're going to do this in lab in a few minutes anyway, so there's no point doing it twice. We'll import the package. And so notice the style of importation here. From Matplot library, so that's the high-level package, import the sub package called PyPlot, and we're going to name it PLT. The other way I would do that import, because I'm kind of anal on how I like to write my scripts, I would probably normally write import matplotlib.pyplot, and then I would build all my function calls on that. That's a whole lot of extra typing, but I use the miracle of cut and paste, so I only have to do it a few times. Either way is fine. In this case, the PLT alias is a pointer to PyPlot, which is part of Matplot library. If you bugger up the import somehow, botch it up, what will happen when you attempt to make the plot pink rectangle of you did something wrong? No big deal. Go fix the mistake and continue. So now we'll create two lists of time and speed. They're identical to these columns. It's small enough that you can just type it in one line and proceed. So nothing new here. And now we'll create a line chart of speed on the up-down axis and time on the left-right axis. So in this case, we're going to create an object called myData. And we're from the plot library. We're going to choose the figure. We're going to set the figure size of 10 by 5. And what that's doing is it says square. It's building a rectangle, which is 10 units wide, 5 units tall. And I don't know what the units are. Again, I suggest you do that by trial and error, because it will depend on how you've sized the notebook anyway. It's not pixels. I don't think it's inches. It's some sort of plotting units. If we made it 5 by 5, the plot drawing area would be a square. It might be a little square, and if it's too small, what do? Give up and go over to business school? No. You change it from 5 by 5 to 10 by 10 and trial and error it until you get a size that you like. That's that whole part. Make it big enough to see, but not too big. Unless you can't do anything else, then use the entire sheet of paper in hopes that you deceive the person grading you. Just kidding on that. Then we're going to use the plot function, which is part of PyPlot. The plot function generates a basic line chart. That's all it does. That's the purpose in life. So plt.plot, and what we're doing here is, I call it building the plot. So we're going to plot the time list against the speed list. By convention, the first list is the left-right axis. The second list is the up-down axis. It assumes that each list is the same length. It tests for that. If it's not, pink rectangle of you did something wrong. We're going to set the color to red. The marker equal V is a downward pointing triangle. Line width equals 1 sets the line width, and that has created a basic line plot. If we want to see the plot, we have to tell it to show it. So plt.show. If you go back to the make a plot function that we provided you 3 or 4 or 5 labs ago, you'll see all those features in that. And in that case, it was doing 2 functions on the same plot, or two series on the same plot, but it was built the same way. Constructed the plot, add the decorators. So these markers and the color choice, for lack of better words, I call it a decorator. That's not the actual Python meaning of a decorator, but that's good enough for our purposes. And it draws the picture. Man, that's a really good data model, right? It looks perfect because by design, it's drawn the markers, and unless we suppress the line, it's going to join line segments between the markers. There is no, we have no data to tell us if that indeed is what the value of speed is at 3.5. So that's just a consequence of plotting. So let's look at another version of that where I've reordered the time and speed lists. Yes, sir. Yes, that would be minus 20. I would have to go get a new job. In the plot call, we can have an object called I think it's called title, and then X label and Y label, and those are just strings, and we put in the values for the strings. I imagine you'll get to that in lab. And then my cop-out answer is go back and look at the make a bear or the make a plot, and you'll see how to do that because that has it built in. So to suppress the line, I think if we set line width equal to 0, it kills the line between it, but I'm not positive. So I want to show you the next example. This is the same data as before. The only difference is things have been reordered. The relationship is still the same. At time 4, we have 20 meters per second, and time 5, we have 30. So we preserved the relationship, so the data are undamaged. But now when we make a line plot, everything else is unchanged except reordering the data. You'll see that the line plot, because of the way it's designed to work, it's put all the markers in their correct locations, but it draws the joining lines from marker to marker, and that is really hard to interpret. So keep that in mind, because you might do that at some point in this class or in the future. Occasionally you actually want to do that, but usually you don't. So that's my one example of how line charts can be somewhat deceptive if the data are not working. If we just wanted to see the markers, we would use scatter plot, which is a different function in Matlab library, and it would just put the green markers in. Without the lines between them, it would look the way we expect it to. Everybody would be happy. Now one of the main points of doing that is to be able to make some inferences about the information that we're plotting. So here we're going to estimate the acceleration using a naive estimation model. We already know the acceleration is not constant, so we're going to come up with some average. And we could estimate the acceleration by defining dvdt, which is the definition of acceleration. Oh, and this will get to your question, actually. So we're going to create a plot title called average acceleration. We're going to have our series names called data and model. Model Y will be the smallest of the speeds. Model X will be the smallest of time. We generate the plot figure drawing canvas, and we're going to plot time versus speed in red. Marker V, line width 1, and then we're going to plot the minimum speed, maximum time in blue. Also, line width equals 1, so it's just going to be a solid line. We'll put the label in, X label, that's a string. Y label, that's a string. We'll throw the legend in, which is series name, so it'll tell us that the red one is data and the blue one is the model. Throw in the plot title, and then let it rip and make the plot. And if we do that, now obviously that's not something that your first time out the gate is going to come naturally to you. Any guesses where I got the script for that from? Your guess is correct. I went to the mighty internet and found the simplest looking one, copied and pasted it. And to this day, I have no idea what I'm doing, but I'm not stupid. Neither are you. Plot.legend series name. Okay, I know what that does. And I assume I can control the corner it goes in. And furthermore, as I need more functionality, I will Google search. So here's our first attempt at average acceleration for this particular data appears to be 7.6 meters per second. And it's an average because at the left edge of our series, we see the acceleration is less than 7 meters per second. When we get off there to the right, we see it's quite a bit more. Now, how can I make those statements? Not data science, physics. The slope on the right side is steeper than the blue line, so the acceleration has to be bigger than 7 meters per second. The slope on the left side is lower than the blue line, so it's less than. And again, I can tell that really quickly in the plot, far faster than looking at the actual numbers. Our friend Pandas also has plotting tools built into it. And so here's an example showing how to do it by using Pandas. It's no simpler than Pandas in my opinion, although I will admit that the syntax is a little bit more straightforward. So here we're going to use a few samples from Pandas. So let's suppose we had the database from census18.csv, which I think you used in the last lab. And so import pandas as pandas, read the database, get the head off it, let it go tumbling down in front of the Bastille. So that's what headless stuff is for. And finally, we want to plot age versus 2010. So we're telling it for our left-right axis, use the age series. For the up-down axis, use the 2010 series. And by default, it's going to associate each element with one another first. So for example, age 0 is going to have this 395-1330 and associated with it. Age 1, 395-7888, and so on. And it draws our plot. If we want to get fancy and throw a second plot onto the same axis, we use line plot and we set it onto an object called AX. And I believe that actually has to be the name of the object. And we can then do our data frame and plot our line age versus 2014, throw a label in, make it red, set axis equal to X. And now we have them both on the same axis. So multiple axis Panda plots are quite a bit easier to construct. To do the same thing in Matlab library, we have a lot of multiple calls that have to be built into the function. It's still doing the same thing, it's just someone else has done the work. Oh, it looks like I'm doing the same in Matplot library to show. So there is the same plot made from the data frame, but using Matplot library. In the case of Matplot library, we have to generate two plots after we've built the drawing canvas, put the legend in, and then show it. So it's not that much more work, but it's admittedly far harder to remember than using the AX feature. So my guidance to y'all is don't overly stress trying to remember how to do this stuff. Remember that you can do it, and remember that the mighty internet has worked solutions to it. And then from those, you can beat it into the problem that you have to produce a plot for. Because that's what I do, and it's unfair to expect you to memorize that. Are there any questions? He asks facetiously, knowing that nobody's going to ask any because you're still 20 minutes ago. Okay, so let's take a quick look at today's lab. Hopefully this is going to render correctly. Good. I just modified the lab this morning, not to get it to go to the right place because it was serving the wrong lab. So your first one is going to be producing plots, and we're going to use the make a plot or the make two plot function, which we played with before. But now presumably you know what most of the pieces are doing. It's no longer just gibberish. Well, maybe it still is gibberish, but it's more meaningful gibberish than it used to be. And in this case, we're going to produce some functions. One's called linear, another one's called quadratic, power, and so on. And then make some plots and explore it. Now, so these examples right here, those have interactive input. That's obviously a piss poor choice of intercept and slope for those red markers. Your job in the lab will be to try to get the line to go through it better than that. And what you ultimately will discover is these ones that have curvature in it, you can probably make fit the observations better. And then you have an exercise, another example. Oh, that's good. So that's actually a whole different context. And then the exercise associated with it is you get to go and design drugs. So all those of you that are drug addicts or want to be, here's your chance to figure out how to dose yourself. You have to see if a linear model gives you better dosage than a quadratic, than a cubic, than a power law model. Then you decide which one is the best and use your model to predict behavior. And this is exactly what they did when they were making COVID-19 viruses, vaccines. And then finally, some playing with interpolating polynomials. By the way, for the recording, that was not an unintentional slip of the tongue. I did that as a joke. Okay. If there are no questions, we'll see you in about 10 minutes on the mighty internet.